So this is section 2.6, exercise 40. This is an angle of elevation thing, it says. So they give us a picture. We've got our airplane up here, and we're told it is 5 miles high. We're told that is some angle theta. And it says an airplane flies at an altitude of 5 miles toward a point directly over an observer. So this is our observer right here. And kind of looks a little bit like a duck, I think. The speed of the plane is 600 miles per hour. So it's moving in this direction at 600 miles per hour. And find the rates of change, find the rates at which the angle of elevation, theta, is changing when the angle is 30 degrees, 60 degrees, 75 degrees. Okay, so if we can do it for 30, we can probably do it for any of the others. We need to relate this angle here with the plane's position, I guess. So if this is at x, then that simply looks like a tangent sort of thing. So I have tangent theta is equal to 5 over x. Now I think I'd rather write it as x tangent theta equal, 5 over, is equal to 5. Okay, so I've related the position of the plane, it's here at x5, and to that theta, just using the tangent. Okay, and like I say, I think I'd prefer to write it like that. And so then, well, we can take derivatives, and we get a product rule here of when we take our derivative with respect to t. So I have dx dt times tangent theta is equal plus x times the derivative of tangent theta with respect to t, and that equals, well, the derivative of 5 with respect to t is 0. Okay, so we have dx dt, which we happen to know. We know that's minus 600 because it was coming in toward our reference point. So I could go ahead and write that, minus 600 times tangent theta. Now we actually even know what theta is. It's 30. But I'm just going to leave that as tangent theta for the moment, plus x. And then derivative of tangent, so we've got our chain rule. We first take the derivative of the tangent of something, and then d theta dt. And derivative of the tangent is secant squared of theta, and then times d theta dt is equal to 0. And this was at 30 degrees, or pi over 6. So if I move all this stuff over to the right, I have x. Do I know what x is? Find the rates when the angle is 30 degrees. I'll have to figure out what x is. I have my relationship here, right? X is 5 over tangent theta. So I guess I'll need to write that in there. So I have x secant squared of pi over 6 times d theta dt is equal to 600 tangent pi over 6. And so, solving all this, now remember that x equals 5 over tangent of pi over 6. So when I divide by x, it's like multiplying by tangent pi over 6 over 5. And so we have d theta dt is equal to, well, oops, got that a little close again. We have our 600 over 5, and we get tangent of pi over 6 quantity squared. And then we have the secant squared we divided by, but 1 over secant is cosine, so we have cosine squared of pi over 6. Okay, well, our pi over 6 triangle, so if that's pi over 6, I know that we have 1, 2, and the square root of 3. So the tangent is 1 over the square root of 3 here, and the cosine is square root of 3 over 2. So that is, well, 600 over 5 is 120. And then we have tangent, so we have 1 over the square root of 3 squared, and cosine was the square root of 3 over 2 squared, so square roots of 3 will cancel each other out, and we'll get a 1 over 4. So, amazingly, we get 30. Now, I wouldn't have seen that coming. So our angle of elevation is changing at and that will be in radians. I had to think about that for a minute. That should be in radians, and it is really radians? Let's see. Oops, quit that. Wasn't watching, sorry. Yeah, I guess that's radians. D theta dt, yeah, radians per second. So 30 radians, that's a lot. Where is, let's see, so this was, I just want to look at what x was here, just because that's really weird. Okay, so x, 5 miles out, and this tangent was 1 over the square root of 3, so it was only square root of 3 is like 1.7, you know, so this is like 8.5 miles out. Well, it's going 600 miles per hour, so 600 miles in an hour is 10 miles in a minute. Okay, so it would have taken less than 60 seconds to change from, see, this is, you know, this is where I really want to think about these numbers. So we changed from an angle of elevation of pi over 6 to an angle of elevation of pi over 2 in less than 60 seconds. And so, oh, yeah, okay. 30 radians per hour, right? Because this is in miles per hour. So, you know, it's helpful to think about your numbers, because 30 radians per second, that's really fast. I mean, that's flying around. Well, they are flying, it's a plane, but I mean, that's really going. So that just didn't seem right. But actually, yeah, at 30 radians in an hour, right? Well, to get radians per second, I would have to divide by 3,600. Okay, so that would be much smaller. So it is 30, but these units, radians per hour. Okay, so, you know, a little trouble at the end, but again, I could sort of go back and redo this and do it really fast and make it look like, oh yeah, that Hillary's so smart. Yeah, but that's not the point, right? The point is that when you really are doing problems, you have to think about these things, and you have to check yourself. And, you know, when I started thinking about 30 radians, I mean, you know, because it's just 2 pi, or about 6 radians in a whole circle. You know, this was 5 times around a circle per second. No, that's way too fast. But, you know, then after I thought about it a little bit and what was going on, we got the units in the right thing, so radians per hour. Okay, so that's 40A, and of course for 40B or 40C, all we need to do is we just need to change that angle. Okay, so you know, these other calculations would be similar. We would have these same relationships here. We would have x and secant squared and d theta dt and so forth. We need to go back and change those angles, which will also make x change. Okay, so I'll just do a 40A, but similar answers for 40B and C.